Hey everyone, my name is Rohan Senapati, and today I'll be offering you a geometric exploration of generalized Mandelbrot sets. So before I begin, I just want to point out that all of the images in this presentation were generated by me for the purposes of computational evidence as part of my research. This, however, excludes those found in slides 5, 6, and 16, which are not my images. Okay, so the Mandelbrot set is a set of complex numbers that remain bounded after taking iterates of the polynomial f of z equals z squared plus c, generating a sequence. It is a beautiful figure that illustrates the intricate relationship between complex numbers and fractal geometry. The Mandelbrot set was first discovered by Benoit Mandelbrot in the late 1970s. During this era, mathematicians were trying to find ways on how computers could complement their research, resulting in areas of interest such as data visualization. Mandelbrot was working on a phone line transmission problem, analyzing a plot of failures over time. Coincidentally, as he was working on this problem, he was reminded of the Julia set, discovered by Gaston Julia in 1918. This reminder led Mandelbrot to the notion of fractals. Fractals are self-replicating figures that repeat on infinitely many levels, giving rise to beautiful figures. Today, real-world applications of fractals include movie and game animators, apartment designs, and the context of nature. Mandelbrot's findings are extensively documented in the fractal geometry of nature. His work was a basis for advanced research in fractal geometry. Despite numerous computational estimates, an exact expression for the area of the Mandelbrot set still does not exist. Subsequent research attempts to give estimates using complex geometry and computation. My research extends the study of Mandelbrot sets by analyzing the generalization of f of z equals z squared plus c to f of z equals z to the power of j plus c. By plotting these generalized Mandelbrot sets using computational simulations, I generalized trends regarding the Mandelbrot set area approximations. Additionally, I explored the structural properties, including the rotational and reflectional symmetries. Finally, I recorded and proved these key symmetries, whose proofs are not systematically documented in literature. My paper begins by establishing definitions and preliminaries necessary for understanding how the Mandelbrot set works. The next section highlights a formal proof of the escape criterion, followed by the escape time algorithm and numerical area approximations. Conjectures regarding generalized trends for the area and escape radius and symmetry are made based on computational evidence. Finally, I derived lines of symmetry and rotational and reflectional symmetries are proved. My paper concludes with some unique and interesting petal-like properties exhibited by the generalized Mandelbrot set. So to recap, what is a Mandelbrot set? Specifically, it is a mapping of complex numbers on the complex plane represented by the polynomial f of z equals z squared plus c, where z sub 0 equals 0, which is the zeroth iterate. It iterates over z sub n, the nth iterate, starting with 0, creating a sequence of complex numbers that lie in the Mandelbrot set. And here are some beautiful pictures of the Mandelbrot set. Now, how do we measure its area? Well, unlike its infinite perimeter, the Mandelbrot set has a finite area. To this day, the area of the Mandelbrot set to mathematicians is unknown. Its estimated area is 1.506484 square units. However, by running simulations, approximations of the area can be made with the escape time algorithm, using tools like matplotlib and code. To create the escape time algorithm, we first generate a complex matrix, which will be our complex plane, using a tool known as NumPy vectorization. We first start with the zeroth iterate, then iterate over f of z equals z to the power of j plus c. The last step is to check whether the point escapes the ball of radius 2 within the number of iterations set in the algorithm. More formally, this is known as the escape criterion. And by finding the proportion of the members of the Mandelbrot set to the total number of pixels in the complex matrix, we can multiply this result by the complex matrix dimensions to obtain the set's area approximation. The following conjectures are derived by running the escape time algorithm for generalized Mandelbrot sets. for several values of j. For each value of j, I computed its corresponding area approximation. To ensure accuracy of the area approximations, I ran the algorithm for different parameter values, specifically the number of iterations and pixel density. By increasing the number of iterations and pixel density, the area approximation becomes more accurate. Accuracy is generally expected to increase as the number of iterations increases, because the algorithm has more time to determine whether the points belong to the Mandelbrot set. Similarly, increasing the pixel density improves the resolution of the set, reducing sampling errors. After a certain number of iterations, approximations stabilize, indicating consistency, which lets me know when to stop running the algorithm for an area approximation. I averaged the stabilized approximations and recorded them as my area. Finally, I create a table representing the coordinates in the form j, area, and then from there, I plotted these coordinates on Desmos and calculated the best curve that generalizes the j versus area trend. Conjecture 1. The degree j and the corresponding area approximation of its polynomial form a general trend fitting a curve. The best fit curve is based on my table of values given below. So note that this result is not an exact result. It's more like an empirical formula generated based on my computational evidence. Conjecture 2. For extremely large values of j, the Mandelbrot set is bounded by the unit disk. Observe that for smaller values of j, the boundary of the set is jagged and exhibits a gear-like structure. And as j increases significantly, the curvature of the boundary becomes more uniform. Conjecture 3. As j increases, the radius of the ball decreases. This is simply a consequence of my previous conjecture. We know that the escape criterion of the Mandelbrot set is that it is contained in a disk of radius 2, which can be proved via induction. However, my results from my previous conjecture showed that for significantly large values of j, the Mandelbrot set is bounded by the unit disk. This suggests that as j increases, the radius decreases. And finally, my last conjecture. As j approaches infinity, the area approaches pi. This conjecture is reinforced by conjecture 2, where I found the Mandelbrot set to be bounded by the unit disk for extremely large values of j. We know that the area of the unit disk is pi, and by graphing the curve and the line y equals pi, we can visually observe the asymptotic behavior at pi. And as j approaches infinity, area approaches pi. I would like to discuss further unique properties of the Mandelbrot set. So the set to the left is represented by the polynomial f of z equals z to the power of 20 plus c. So as you can see, it clearly exhibits rotational symmetry, and looking closely, it appears as if a group of 19 people are standing in a circle. These 19 people represent the number of petals or regions in the polynomial, which is one less than its degree. And the notion of petals led me to make a connection to roots of unity and derive reflectional and rotational symmetries. A set of degree j has both j-1 petals and j-1 roots of unity. So notice how the roots of unity are elegantly inscribed in the jth Mandelbrot sets. More specifically, for a set of degree j, a j-1 gon is inscribed in it containing j-1 roots of unity as its vertices. Using basic geometry, we can derive the lines of symmetry. And proving that the jth Mandelbrot set is symmetric across the derived j-1 lines for these specific cases requires two technical lemmas or secret ingredients. The first lemma, each of the pairs j and r must satisfy this condition, where the radius of the complex number before the transformation must be equivalent to the radius of the complex number after the transformation. The second lemma, each of the pairs j and r must satisfy this condition. If we were to take the transformation of the complex number raised to the jth power, this must be equivalent to taking the jth power of the entire transformation. Capital R is the reflectional symmetry formula, and lowercase r is the rotational symmetry formula, which again we can derive using basic geometry. Note that some cases like rotation and conjugation have been observed in the past. I'm contributing by giving proofs of the reflection cases using explicit algebraic formulas. Finally, I would like to address broader implications. Besides theoretical problems, fractals have real-world applications today, such as cryptography. Their complex patterns can be used to create more secure encryption systems, which is central to cybersecurity. And as I move forward, I'm hoping to apply my knowledge to practical applications in the field of dynamical systems and contribute to the broader field of computational mathematics. Thank you for listening.
Rohan, thank you for that highly technical but still understandable presentation. I haven't seen Mandelbrot sets since my time in college, so this was very exciting. So I guess my first question is about what you said about the area. So you said that mathematicians still don't know the precise area of the Mandelbrot set.
Right, right.
Can you help us understand a little more why that is the case, given that we have an exact mathematical formula and we can run all these numerical experiments?
Well, we don't really have a formula for this. I think the thing to do, the problem is that the Mandelbrot set doesn't exactly have a defined boundary because it is self-similar. Um, the pattern repeats on infinitely many levels, which is why it is hard to identify the area. But however, like you can, since you can't do that, there are methods, like I've explained in my presentation, where we can find numerical estimates and then generalized trends.
I see. So you're looking at the asymptotic behavior of the numerical results to
Yes, yes,
compare.
yeah.
And so when you say that mathematicians don't have an exact answer, that just means that there is some error bar on the number you quoted, the 1.5 something.
Yeah, yeah,
Got it. But we are pretty confident that the value is around that value, right?
exactly. But we note that that value is specifically for the polynomial f of z equals z to the power z squared plus c, which is the second Mandelbrot set.
I see.
My research further extends that by finding area approximations and trends for like several values of j, and then generalizing the curve.
I see. And you showed these intriguing results about the symmetry properties of these sets. How did
Yes.
you land on these? How did you find out that these symmetries existed?
Um, so what I did was first I was able to derive my conjectures based on like the computer simulations. After I did that, like I took a closer look at the Mandelbrot sets, and then so for a while now I've been studying complex numbers, like for the past year or so, and roots of unity is a pretty big topic in this field. So I was able to analyze the Mandelbrot sets, and something clicked. It looked really similar to the roots of unity, and I was able to establish a pattern and then draw out the roots of unity manually on each of the Mandelbrot sets that I presented in the slides. And yeah, I was able to make a connection there.
Got it. And finally, you mentioned cryptography. Can you help us understand how Mandelbrot sets and fractals are relevant there?
Well, I haven't really done any research on this area as of now. I just happen to know that it has applications in cryptography because the Mandelbrot sets are so complex, like their patterns are like you know that they're self-similar, which means that they repeat on infinitely many levels, as I explained. So that's why um it's it would be really secure to be used in like say an encryption system using a complex pattern generated by fractals.
I see. So the idea is to use them for even more secure encryption methods.
Yes.
Got it. So, final question, what inspired you to study fractals?
Uh, so for a long time, I have been interested in competitive mathematics, and I think just recently, like over a year ago, I came across the field of complex numbers and fell in love with it. So complex numbers is foundational to the study of Mandelbrot sets. So as I solved more problems and gained more intuition regarding complex numbers, I was able to find patterns and eventually came across the field of fractals.
Sounds great. Well, I first learned about complex numbers, well, the science behind complex numbers more in college. So it's definitely an early start you are getting there.
Okay.
And it was a very insightful presentation. And thanks so much for sharing all your insights. And hope you will have a chance to make that jump into cryptography and
Yeah. Yeah.
use
Thanks.
it there.
Thank you.